All right, this morning we're going to pick up where we left off last time and discuss random forest hyperparameters. So at the end of our last lecture, we introduced what they are, talked about the relative importance of them in terms of when you might want to tune them, when you might not care so much. So today we'll go into that in more detail, and we'll actually see through working with our familiar example, the Ames housing example, what happens, what kind of improvements do we maybe get when we actually do tune random forest hyperparameters. So recall the list of them, and it's in rough order of importance, but I'll group them again here in a moment. The first hyperparameter is number of trees. This is in some sense both the most important one, but also the first one because you're going to set it, the values of it before you do any model building. The second one is mtry, which recall is the number of features to randomly select when doing splitting. The third is tree complexity. So how complex do we grow the individual trees that we're going to aggregate together? The fourth is the sampling scheme. So we'll see that we can actually adapt bootstrapping. We don't have to use the standard bootstrapping sampling scheme, and we can change that around a bit if we'd like. And the fifth is the splitting rule, which, as mentioned last time, usually won't have much effect on model performance, but may affect runtime if we need to be concerned with that. So we had said that 1 and 2 we call these tier 1 in the sense that these are the most likely to have an effect on model performance, and they're the ones we definitely want to tune when possible. The third, and fourth were tier 2. They are interesting perhaps to look at, and the fifth one is tier 3. As mentioned, it won't typically affect model performance very much, but it may be useful in terms of computational considerations. Okay, so let's go through these, discuss each of them, and then look at what happens in our example. All right, so we'll begin with number of trees. We'd already seen this is presumably important when we talked about bagging. Before we introduced random forests and split level randomization, we did see that we typically want to increase the number of trees until we get some sort of error stabilization. So just a reminder there, so it needs to be large enough for the error to stabilize. So in particular, if we plot loss function, our error measurement, against number of trees, so number of trees against the loss function, what we want to see there is some sort of asymptotic error stabilization. If we're still seeing a decrease, then that indicates we should probably keep going further and increase the number of trees. Just like with bagging, there's no such thing as too many trees. Is not a consideration for performance. Okay. So we can't over aggregate. We can't get, say, an overfitting from using too many trees. What is for computation, right? So at some point we don't want to just keep adding more and more trees, because if we're not getting any real improvement over the error, well, then we're just costing ourselves computation time, runtime, at no real gain. Okay. So we're looking for a balance, right? We want a balance or we might say sweet spot. Basically, what we'd like to use enough trees so that we see error stabilization, but not too far, not too many after that. We don't want to waste too much time being sure that we're not going to gain any additional improvement. Okay, so what should we start with? Well, a good sort of rule of thumb starting point is 10p, where, as usual, we're using lowercase p to indicate the number of features. So however many features you have in your data set, multiply by 10, and then start there. Okay. And you may at that point already have enough trees for error stabilization. But if you don't, then just keep increasing for a while. You keep trying some different values. Now, one important point here is, and we'll see this, but also we'll especially see this, well, later on, not today, but as we look at models in the future with more tuning, the optimal number of trees so if we tune this initially, we may reach some optimal number of trees, but as we tune the other hyperparameters, it may change. So the optimal number of trees may change as the other hyperparameters are tuned. So just something to keep in mind that you may want to go back and take a look again later after you've, say, tuned everything else. Do you want to perhaps change the number of trees again? All right, so with that in mind, let's take a look at our example. So as mentioned, we're going to keep working with the Ames housing data that we've seen before. Okay, so in the Ames data set, the number of feature variables is 80. Okay, so 10p in this case would be 800. So what we're saying then is 800 trees should be kind of a reasonable number to look at. And in fact, what we'll see is that the out-of-bag error stabilizes around there. Okay, maybe. So here's what I mean by around there. Now, where is it exactly? It's hard. I mean, there's no clear answer to that. But if we take a look, we look at this graph. So here on the horizontal axis, we have the number of trees. And on the vertical axis, we have our out-of-bag error, the root mean square error estimate. And so we see that it's certainly, we want to go past 500. Maybe we'd say it's stabilizing around 750. Is it dropping more at the end as we get closer to 1,000? That just, I mean, that's not really a big change. So certainly around 800 is a reasonable estimate in this case. So is 250 good? Well, it's a little, of course, hard to read on the graph, but I'd say that you're still getting a drop, right? You notice like at 250 and say down to 750, there's definitely a decrease there. Maybe it's not an exceptionally large decrease, but maybe several hundred in error. I don't know. So if I looked at this, if you ran this model with 250 trees and got that graph chopped off at that point, you might say that's good enough. But I would suggest probably you'd want to go out a little bit further. So this is probably a case where the computational increase from say 250 to 750 is actually not going to be that bad for most systems, unless you have an extremely large data set. So at that point, I would say that this is a good place to see where like the 10p rule of thumb is nice, because it confirms that you really aren't having. Part of this, right, is you want to go, let me say, not too much further. All this is, of course, very rough, but in this case, we haven't really seen much of a change, say, from 500 out towards near 1,000. So at that point, 800 seems like well kind of past the point where we can say, oh, yeah, we're pretty good. So I think this is kind of a good argument in favor of that. At 250, it's not entirely clear maybe that you're not going to get another drop later. But we've gone far enough out of this point that I think we can say, yeah, we're probably, nothing's really going to happen here. All right, so going back. So that's for number of trees. What about our second hyperparameter, which is mtry? So just as a reminder, what are we talking about here? So mtry is the number of features that are randomly selected to consider when performing each split. So for this is what we call the split level randomization. We're randomizing at the level of the splits, hence the name split level randomization. Okay, so what can we say here? Well, of course, we can tune this, but can we make any general observations? So what happens when we consider lower values of M-try, so ones which are smaller? Okay, so if we're, say, close, not necessarily 1, but close to 1, or just relatively small compared to the total number of features. Okay. Well, so in this case, you're inducing more randomness because you're going to have, you're selecting less features, so any individual feature is less likely to be selected, right? Because it's random. It's just simple random sampling on the features. So what's this going to result in? You're going to get less tree correlation because it's more likely that the trees are going to be much different from one another. Because from one tree to the next, it's much less likely that you're going to have the same features showing up in the splits. But because of the extra sort of level of randomness here, you're going to end up typically having weaker predictability. And this is simply because if there are features which are important, you're less likely to pick them, right? You might miss them. Okay. But if you have lots of features that are important or relevant, that have something to do that give some predictability, then this can work well. So so this can be better if there are many relevant features. So if lots of the features will give you sort of good splits, one thing that will indicate is if you have a lot of relevant features, there's a good chance the relevant features are correlated with one another, right? So this is a case where then you want less tree correlation, and you can get that in this way. Okay. So what about higher values? What does that do? If we get closer to bagging, so picking all the features, or we just pick many of them, what's this? Well, this is good for what we might describe as noisy data. So specifically, if there are lots of irrelevant features, and this is typically what introduces noise in a data set. There's lots of kind of information in the data set that isn't actually telling you very much, right? That's kind of what we mean here by noisy. There's not a lot of signal. So if there are lots of irrelevant features, so ones whose values don't really carry much predictability, what we want a higher chance of selecting the relevant ones. So in other words, ideally we're not going to split on irrelevant features, right? But if we use a low value of M-try and we have a lot of irrelevant features, then it's possible that all the ones that get selected for the randomly selected for the splitting, that they're all irrelevant, and that wouldn't be good because then we're just going to split in some way that doesn't really carry much predictability. Okay. So then the solution is to select a higher percentage of the features so that there's a more likely chance that we do pick relevant ones. So just as a reminder, the standard default M-try values are the following. And these tend to perform reasonably well. As mentioned last class, we're talking about tuning random forests, tuning the hyperparameters, but they do perform. Random forest algorithms tend to perform well off the shelf in the sense of without any tuning. They still deliver good results, but you still do. I mean, you'll often get improvements by tuning, and so you don't want to just say, oh, okay, since it's good off the shelf, we shouldn't tune it at all. Okay, but the point is that even if you don't, or you do minimal tuning, you should still get reasonably good results. So just as a reminder, mtry for classification is you take p over 3, so a third of the number, or sorry, for regression, the number of features, and then you take the floor, so the next integer down. So it has to be a whole number. And for classification, the standard is to take the square root of the number of features and then take the floor of that. Now, how much do you want to tune? So would you want to, for instance, check every integer between 1 and p? Probably not. That's probably a little excessive. Okay. So, so basic rule of thumb for tuning mtry. So what kind of grid search do we want to look at here potentially? So start with 5 approximately evenly spaced values from 2 to p. So you typically don't want to use 1 because you don't want to randomly select just a single feature. You want to at least give the algorithm something to compare to. So if you pick 2 features, then at least it looks at both of them and then considers the splits and chooses one. Okay. But you're going to probably not get your optimal performance at 2. And so then space them out. Again, this is just approximate. They don't necessarily have to fit exactly, but that's good enough. Just you want to kind of create some range and test some values across that range. Now, there's no need to only stick to 5. If you wanted to try more, you could. Okay. So keep in mind that since we're doing multiple hyperparameters, you're going to probably end up doing some sort of grid search. So for instance, essentially, you're going to create some higher dimensional sort of grid with values of the number of trees, the number of mtry, and other parameters, and then you're going to run a search across that and try to kind of, if nothing else, if all you do say is tune number of trees and mtry, and then you're going to want to sort of test pairs, right? But then say if you include some parameter for max depth, then you're going to have like triples, and so this of course is what you get into with hyperparameter tuning. And so that could expand to a large number of possibilities fairly quickly. Anyway, so that's just a kind of long comment about that. What about in the setting of our example? In that context, what do we come up with here? So back to the Ames housing data. Okay, so here the default is, so this is a regression problem. So it's going to be p over 3. So we're taking the floor of p over 3 rather. So the floor of 26.7. So remember, the floor always rounds down, so 26. So that would be if you were going to run, I would say, the random forest algorithm using one of the packages such as Ranger or Random Forest, it's going to use 26 as the value for mtry. Okay, but what do we actually see if we try some other values? Let's take a look. Oops. There we go. All right, so what we're doing here is we're graphing number of trees and against the out-of-bag error, the root mean square error again. But what we're seeing is we have different graphs corresponding to the different values of mtry. Okay. So they all roughly stabilize in the same way as before, around 750-ish or 800. Notice that we get a very large error if we only use 2. And we get 80, of course, is the number of features. So that's basically the bagging error. Okay. We see a slight improvement. So 26, the default, performs actually very well. We also look at some other values here, 21, 41, and 60. 21, so it gives a slight improvement over 26. And then, well, 41 doesn't really, it's about the same as 26. 60 is a little worse. Okay, so what do we see about with this then? Split level randomization, so the kind of playing around with mtry, improves over bagging. Bagging is the second worst error, although it's certainly much better than, say, did 2, which is just way too random. That's the idea, right? A small value, a really small value for mtry, like 2, is probably not going to perform too well because it's just too random. But slightly lower than the default here does make some improvement, although not particularly large one. So another kind of indication that you'll get good performance often just sticking with the defaults. So we'll just make that comment. So, so mtry equals 21 improves, but only slightly, over the default mtry equals 26. Okay. Oh, so there was a question in the chat, which was all of them shoot up at the end. Is that overfitting? No. So they're not shooting up. That's just a line. There's a little lines indicating. Sorry, I'm not going to bring the picture back up. All that was indicating was that's the number that corresponds to that curve. So those are just connecting the. They're not actually part of the graph. No, they all end basically flat, and then that's just was trying to indicate which number of features correspond, what value of mtry corresponds to which line. You can also see them by the color, but if the colors aren't showing up, that was the idea there, was to indicate that. All right, so now we get into the sort of less important ones, but there's still, of course, things to say here. So tree complexity is next. And essentially, we have the same considerations here as we had for individual decision trees. How do we control tree complexity? Okay. So we can control the complexity, aka the depth, of the individual trees. Okay. So there's not really too much new here. So there are several choices of tree-specific hyperparameters to tune here. Okay, so maximum depth. So explicitly restricting the depth that the tree can grow to. Minimum node size. So forcing the tree to stop splitting if it would make any it would make the nodes too small. So in other words, you'd have terminal nodes that don't have enough observations in them. Or there's another way to do this, which is just to set a maximum number of terminal nodes. So force the tree to stop splitting if the number of terminal nodes would grow past some fixed point. Now, tuning minimum node size is the most standard approach. And one of the reasons for that is, in some sense, it's the most flexible of the three. because we've seen examples when we were discussing, say, individual trees, where we grew a tree and the number of splits wasn't completely symmetric. So at some point, maybe it stopped splitting a little bit earlier, but then another, depending on what branch we were in, it split again later or did not. And so that will happen when you tune minimum node size, because there's no reason that the splits, of course, have to be symmetric in terms of the number of observations on each side. Right? We're splitting on loss function, not on just trying to create two equally sized partitions. Whereas maximum depth, well, of course, does exactly what it says. It's kind of brute forcing it a bit, and it's not kind of paying attention to the individual nodes. And same thing with a maximum number of terminal nodes. If you run those, use those kinds of hyperparameters, then it's certainly possible that you'll get some nodes that don't have very many data points in them, and therefore kind of give somewhat overfit predictions. So this is probably the argument in favor of tuning minimum node size. The defaults are 5 for regression. So in other words, you want to have, we're saying we want to have at least 5 data points, target values to average together, because that's what we're doing with the regression prediction. We're going to average the values of that node. And in fact, for classification, we only require 1. So we don't of course, we don't want any empty terminal nodes, any empty leaves. But for doing classification, we can always just classify to whatever's there. Remember, we're using plurality vote or perhaps class probabilities, and that's fine. Now, certainly we might want to tune that, and it might turn out that better than 1 works in a classification problem. So in general, what we can observe, increasing minimum node size helps decrease runtime. Okay, why is this? Well, if we stopped splitting earlier in the process, that will take, the algorithm will take less time to run, with minimal increase in out-of-bag error. So you don't lose much in terms of performance by keeping the nodes relatively large, and therefore not splitting down further, not going deeper. Okay. So let's take a look at an example. We're using, this isn't actually specific to the Ames example, but this is typical of what will happen or can happen. Okay, so what's going on here? This time on the horizontal axis, we're graphing the minimum node size. We're plotting minimum node size, and then we're plotting it against how much on the left, how much percent growth we're seeing in the error estimate. So how much is the error going up by if we increase the minimum node size? On the right, we're graphing against the percent reduction in runtime. So notice that as we increase the minimum node size from 1 to 5 to 10 and so on, the error is steadily going up. It's getting a little bit steeper, in fact, towards the top. But notice that the growth in error is not that much, even like all the way up on the right-hand side at 20. You're only seeing about a 3% growth in your out-of-bag error. On the other hand, the impact on the runtime is much more considerable. So we see that compared to just using a minimum node size of 1, as we get towards 15 and 20, we've reduced our runtime by almost over 40%, almost 50%. So say it looks like the optimal reduction in runtime is around 17 or so. And so we might want to stop there, but maybe we want to go to maybe 15 would be reasonable, right? So if we use 15 as our minimum node size, we're getting less than a 2% growth in error and over like a 45% reduction in runtime. So that would be perhaps a good argument in this setting, whatever this example is, to do so. So the other, where do you maybe can you get any kind of performance improvements from increasing the minimum node size? Well, it can also help with performance when working with noisy data and large values of mtry. Okay, so two aspects to this. If you have noisy data, you'd probably want to have more data points rather than less at the nodes when you're calculating predictions. The other thing is if you're considering lots of features because you're working with noisy data, you probably want to have a good number of data points at each node when you're creating splits, so that you're not just splitting on the noise, right? You're not, because you're going to assess lots of features. You don't want to just take one and then split on it because of the noise in the data. So this will kind of this is more likely, a large value for a minimum node size is more likely, well, is better for preventing that from happening. It makes that less likely to happen. So you don't want to chase bad data, basically. And if you have small numbers of data points at the nodes, you're going to end up chasing them. If there's no, you're going to chase after those points because you have no other option. So if you want to prevent that, make sure that you have a reasonable number of data points at each node so that you can kind of aggregate together. Okay. The fourth hyperparameter we discussed was sampling scheme, or discussed when named. So what do we mean by changing the sampling scheme? And what impact does this have? Okay, so the default sampling scheme for random forests, well, we already know what it is. It's bootstrapping. Because remember that if we set mtry equal to p, that'll take all the features, then we're just doing value, which of course is based off bootstrapping, or if you like, bootstrap resampling. Okay, so just a quick reminder of what bootstrapping involves. We use random samples. So all points are selected completely at random from the training data, drawn with replacement. So points can occur more than once. Of the same size, and approximate distribution, as the training set. Okay. Now, if we want our data set, or if we want our resamples that we're going to grow our trees on to be the same size as the training data, then there's not really anything else we can do. Because if we want them to be the same size, we sort of have to do it with replacement, because otherwise all we do is be using the training data over and over again. That wouldn't work. Okay. But we can adjust. We can adjust the size. Okay. So we can choose samples which are smaller than the training data set. And then if we do that and we make them smaller, we can also consider with versus without replacement. So if we're picking, say, samples that are 50% the size of half the size of the training data, then we could sample without replacement, because then we'd still get different samples by doing that. So just make that point very explicit. So to sample effectively without replacement, we must decrease the sample size so that our samples are actually different. That's what I mean by effectively here. So typical is 60 to 80% of the original size. So if lower values of sample size what advantage they have is they result in reduced tree correlation. Because the smaller the samples get, the less likely that they're going to look like the original training data and hence like each other. So in a situation where you'd want to do this, maybe when you're using values of M-tri that are close to P. Okay, so this can be a good choice. With noisy data where M-tri is close to P. Okay, so remember what's the sort of the thought process here. Okay, if we have noisy data, there's lots of irrelevant features. We want a high value of M-tri, value close to P, so that we have an increased chance of selecting the relevant ones. But then if we're selecting most of the features, there's a much higher probability that we're going to end up with tree correlation across the trees, because it's more likely that we're going to select the relevant features at the initial splits, the most important ones. So one way to reduce the tree correlation in that setting, where we do want to select a lot of the features, and we do have run a chance of selecting the powerful features at the initial splits more often, is to choose less of the training data, so that now our resamples look different, more different from one another than they would if we were using all of the data sets which were the same size and so the same distribution as the original training data. Okay. What about sampling without replacement? When might we want to actually do that? So this can be helpful. So we don't want necessarily then, what are we doing if we're sampling without replacement? We're not going to allow ourselves to choose any data points, any observations more than once. So this can be helpful for data sets with unbalanced categorical features. And so what do we mean by unbalanced here? What we mean is that some categorical features have many more possible values than others. So this could be a situation where, like, say, some of your categorical variables are binary, or have just a relatively small number of values, say like there's 5 different values of a categorical variable. But then you've got other categorical features in the data that have, say, like 100 values or something like that, different ones. Why does that matter? Well, because say you do have like some categorical variables that are very unbalanced, so they have lots of different values. Okay. Well, ideally, in your training, in your sample that you're going to train on, when you take your resample for training the individual, say an individual tree, that's going to get aggregated in. you would like it to be the case that most or all of the potential values of that feature do show up somewhere. But if you sample with replacement, and so some data points are getting picked several times, well, in those unbalanced categorical features, you're going to get some of the values showing up several times and maybe other values not showing up at all. Okay. And so that's going to skew things in some weird ways. So let's see the effect of this, that this can have an effect. It might sound like it shouldn't matter, but with the Ames housing data, we actually see this happen. So this data set has several categorical features. With many values. So some of which include neighborhood, quality, zoning, and several, I'll say, etc. Okay. So these are some of the variables in that data set which have lots of potential values to them. Okay. And what we observe, and we'll see this in a moment, is that out-of-bag error estimates decrease somewhat when we sample without replacement. Okay. Let's see. So in this graph, we have two curves. What we're graphing is the error against what percentage of the data, or how much of the how big is the sample relative to the training set. So when we say sample fraction, say 60%, we mean we're picking samples which are 60% the size of the training data. Okay, so there are two curves were labeled false and true. The blue one, which is above, says sample with replacement true. So that's the one where we are sampling with replacement. And one below, sampling with replacement false. We see then that one where we're sampling without replacement actually for relatively large sample fractions performs better and reduces the out-of-bag error as compared to when we sample with replacement. Now, the very left-hand edge of this is basically choosing extremely small samples, and so we see that the error for that is relatively large. So both of these decrease quite quickly, and in fact perform better with samples which are close to the entire data set. In particular, we see at about 75%, we're not getting a huge improvement there. But before that, we're doing much better at, say, 75 to 80% of the data than we are at 50%. So one observation we can get off of this is that the Ames housing data set is not especially noisy in this sense. There's not a huge number of irrelevant features. And so using larger samples is working just fine. We don't really need to go to small samples in order to handle true correlation issues. Finally, we come to the last type of parameter, which, as mentioned, is one that we're not going to see a ton of improvement from, which is the splitting rule. And what do we mean by splitting rule? We mean how we're going to select and assess the splits. Okay, so the default is the CART algorithm, which has been our setup since we talked about individual decision trees in Chapter 9. Okay, So what do we mean by the splitting rule for CART? We mean evaluate all possible splits on the, not all the features, but the M-try selected features, whatever M-try is. We take all the features we select, and then on those features, those are the only ones we're considering. We look at all the splits with the rule. So how are we going to assess the splits? How well which one? Because we're trying to choose an optimal one. How are we optimizing the split? Well, we know that what we're looking at is loss function. So the rule changes for regression or classification. For regression, we're going to minimize sum of squares error at that split. For classification, what we're looking for is we're going to minimize cross entropy or the Gini index. Now, one way sometimes this gets phrased is rather than saying we're going to minimize it, we're going to maximize the reduction in it. That's another one, kind of, it's saying the same thing, just slightly differently. Okay. But in either case, what we're looking for is the best improvement in the loss function. Okay. So why would we possibly want to change that? This default rule, specifically looking at sort of as many or all the possible ways that we can assess the splits on those features, it favors variables with many possible splits. So ones where we can fine-tune the split quite a bit. So the obvious one here are continuous numerical variables. Think back to our first example that we worked through in detail on decision trees. We were splitting on essentially the x-axis for the sine function, right? So there we can sort of split on any value we wanted between 0 and 2 pi. Now, of course, in a practical sense, you're going to limit the number of decimal places you're going to look at. But say you go to 2 decimal places. Well, now you've got lots of possibilities, or even just 1 decimal place, right? You can split on 0, 0.1, 0.2, 0.3, all the way to 6.3 or something like that, right? If we round to that level. That's a lot of possible splits at every different position. Okay. So continuous numerical variables where we're splitting essentially on the real line, that gives you lots of possibilities, lots of ability to sort of tweak it slightly and just change the split a little bit and get an improvement. Sorry, and then, so that's one. Another one is unbalanced categorical variables, where you've got a lot, you can assess lots of different categories. Whereas with a binary one, there's not a whole lot to look at, right? There's just 2 possibilities, and you ask if it's a good split or not. Okay. Okay. There are some alternatives, although there is not really much to say here in the sense that lots of these alternative proposals haven't really shown themselves to actually do a whole lot in terms of improving things. So the first one is what are called conditional inference trees. I'm not going to say much here, and you'll see why. In fact, I'm going to be very kind of non-specific about what this is. Okay, so this is an approach intended to reduce this sort of feature selection bias, where some features are more likely to be split on because they you have this kind of, you can fine-tune the splits more. The splits. Okay. All right, so that might sound at first like, that's good. Okay, we can, if this is an issue that we've identified, we can fix it. There's an issue here. Well, it produces longer run times. And that might not be that big of a deal if we're getting something out of it. But it's also not proven to improve predictive performance, which is disconcerting because we're going to, if we do use this approach, we're pretty much guaranteed to increase run times over cart. But if we're not going to get any gain in predictive performance, then that's really not, doesn't seem worthwhile. Okay. Now, approaches where we do see some improvement are, or well, at least improvement in some part, not in performance, but at least in runtime, or what are called extremely randomized trees. The idea here is that for each feature, randomly select a single splitting value. And evaluate the split on that value only. Okay, so in other words, say for the Ames housing example, we say we pick lot size. Okay, that's a numerical variable. So that's what our feature. What we would do is instead of assessing all the different, say, possible values that lot size can take, and then looking at, is this a good split? Yes, or like essentially creating an inequality on the lot size. Yes, it's bigger than this, or no, it's not, say. Okay. We would randomly select a single lot size, say 1,000 square feet, and ask yes or no on that value without assessing any other possibilities. Okay, so this means that we're doing very few calculations. So not too surprisingly, this produces the fastest runtimes. Extremely computationally efficient. But as the name suggests, it's extremely random, right? Because hence the name extremely randomized trees, because you're random. There can be so many different splitting values, and you're just randomly selecting one of them. Okay, but too much randomness, which is really what we're often going to get here, often results in weakened predictive performance. Okay, so that seems like maybe it's excessive. All right, well, what we can do instead is weaken this idea, but maintain some of the idea. Because it's not a bad idea in some sense to not necessarily assess all the splits. So weaken the idea behind extremely randomized trees. And this is where, when we do this, we're getting into what I kind of had mentioned towards the end of our last class, namely that we can perhaps gain some runtime, some computational improvements without necessarily doing too much in the way of weakening the predictive performance. Okay. So what are we going to do here? So picking a single splitting value is just too random. Okay. So what we do instead is we randomly select a subset of possible splitting values for each feature. rather than just one. And evaluate the splits on these. Okay. So what this will do, so this will reduce runtime versus CART, right? Because CART has to assess every possible split. And hopefully it's not too random. So it won't hurt predictive performance. Too much versus CART. So since CART's going to assess all the possibilities, it's going to find the best one. So certainly we would expect here that we will miss the best one, but maybe by not by too much. Okay. So in particular, it should perform better than extremely randomized trees, which is just, as mentioned, is just too random by only considering that one splitting value. Okay. So the overall then perhaps point to get out of this is that tuning random forests will generally improve their performance. And we saw that in the Ames example in the various kind of assessments we looked at. But off the shelf, so in other words, there's no tuning, is usually pretty good. So in particular, if we were to take the Ames example and just run the defaults of, say, 10p trees, so 800 trees, and the default value of mtri, the performance of that was good. We didn't really gain a whole lot more off of that. And we did see that we got an improvement by sampling without replacement and decreasing the sample sizes, but not so much that it would have really hurt much if we'd not considered that. Okay, so it is worth keeping in mind that as much as we spent an hour discussing tuning, we don't necessarily get a huge improvement off of it. Okay, so the last thing to mention, we don't have much left, but there's not too much to say here, is feature interpretation. We have the same issues that we do with bagging. Okay, so as bagging, the aggregation in the random forest process limits direct interpretability so we consider feature importance. So remembering that feature importance, then this means the same thing as before. but let's just, in some sense. Basically, what we're looking for is how much do the features affect the loss function. Okay, now there's an additional approach here that we didn't have before. So there are two approaches to this. The first is the same as with bagging. Number one is what's called impurity-based. And this is the same, and this is just a fancy name for what we already have discussed. So as for bagging, determine feature importance. By considering the total reduction in loss function right? In loss function by across. Sorry, let me say it like this. So for each feature, across all trees. Okay, and the second is what's called permutation-based. And the idea here is to see how sensitive the features are to the specific values that are showing up. So what you do here is you use the out-of-bag sample to estimate performance. Okay, one second. So what I mean by the total reduction in loss function for each feature across all trees is, say, take a feature like, say, lot size for the Ames housing example, and then over all the trees that you've grown for the random forest aggregation, look at how that feature is affecting the loss function. How much reduction are you getting from that feature, and just total that all up. And then, as before, just create some sort of normalized score. So like VIP, right? In Carrot creates this sort of measurement from 0 to 100 of how much the loss, that particular feature matters in the loss function compared to the other features. So it's just kind of a relative measure of importance. How much did it affect the total reduction in loss function? Okay, so let me just finish this real quick because we're almost out of time. So for permutation-based, you're going to use the out-of-bag sample to estimate performance. You randomly permute the values of the features. Basically, you change them up a bit at random. What you're trying to do is to see how much does out-of-bag performance change if you just tweak the feature values a bit. And repeat. So in other words, measure use the out-of-bag sample to estimate performance again. Keep doing this. And average across all trees for each feature. Because essentially what it's doing is you're saying, are the specific values in the out-of-bag sample what are kind of determining the importance, or is the feature really important? So really important. So a larger reduction implies a more important feature. Okay, so just to see what this does, you often get very similar results from both of these approaches. Here's if you do this with the Ames example, and you use VIP to generate these plots. we have the left, we have the impurity measure of importance, and then on the right, we have the permutation measure of importance on some just kind of scale. Now, in both cases, overall quality ends up being the most important. And then a few of the others bounce around a bit. So neighborhood is the second most important using impurity, but only third using permutation. And the permutation measurement, GR live area, so greater living area, bounces up a little bit. But overall, you're seeing the same features showing up in a relatively similar distribution. So a couple different just approaches to this. But as mentioned, we are limited by just the aggregation to simply looking at feature importance. How does it affect loss function reduction? Okay, so that's the end of chapter 11. On Thursday, we will start chapter 12 on gradient boosting.